Hello students, today we will discuss about uniaxial interference figure. So how interference figure is being produced? We know in earlier discussions that orthoscopic arrangement provides parallel polarized light rays, and through those light different properties of minerals are being studied, and in order to produce interference figure we take use of the conoscopic arrangement of the microscope, where condenser is being used, and through condenser converging light rays are being produced, and by use of that a figure is being produced which is called the interference figure, and this figure is of much use in identifying the mineral and helping the detection of the optic sign of minerals. So let us discuss this uniaxial interference figure. So interference figures are observed in convergent polarized light. So through conoscopic arrangement of the microscope we can get convergent polarized light. So in order to get this convergent polarized light, the petroleo microscope is converted into conoscope or polariscope. And how it can be possible? By use of strongly converging lens below the stage, which is called as condenser. A medium to high power objective is being used. Concave mirror for the reflecting light to the polarizer. Nickels are crossed. Vertical lens is being used. Eyepiece is being used. So in this condition only we can get, or we can convert the petrological microscope into conoscope, and under this condition we get cones of light rays like this, cones of light rays. So these are the parts which are being used. These are the parts which are being used to convert the microscope into conoscope. Without Bertrand lens and eyepiece, the interference figure can be observed, but with reduced magnification. So in order to study the uniaxial interference figure, the following sections are used. One is the basal section, or the section called perpendicular to optic axis. Another section which is cut parallel to optic axis, or it is vertical section. Third is the any other section. So these three types of sections can be studied, and they give rise to different types of figures. So let us study the basal section interference figure, or it is called as the optic axis interference figure. Because optic axis is perpendicular to the basal section. So when you look from the top through the eyepiece, the optic axis is, is parallel to the basal section. So when you look from the top through the eyepiece, the optic axis is parallel to the basal section. So when you look from the top through the eyepiece, the optic axis is parallel to the basal section. So when you look from the top through the eyepiece, the optic axis is parallel to the basal section. So when you look from the top through the eyepiece, the optic axis is parallel to the basal section. So when you look from the top through the eyepiece, the optic axis is parallel to the basal section. So when you look from the top through the eyepiece, the optic axis is parallel to the basal section. So when you look from the top through the eyepiece, the optic axis is parallel to the basal section. So when you look from the top through the eyepiece, the optic axis is parallel to the basal section. So when you look from the top through the eyepiece, the optic axis is parallel to the basal section. So when you look from the top through the eyepiece, the optic axis is parallel to the basal section. So when you look from the top through the eyepiece, the optic axis is parallel to the basal direction of observation, and accordingly name is being given. So optic axis interference figure means the optic axis is parallel to the microscope tube, and definitely it will be perpendicular to the mineral section. So it is basal section to perpendicular to the optic axis, and that's why this section is called basal section interference figure, or it is called as optic axis interference figure. So these are the three types of interference figures which will be discussed in under uniaxial interference figures. Let us see, in convergent polarized light, the light rays are produced in this manner. These are the cones of light rays, cones of light rays are being produced, and these cones of light rays, they hit the mineral section on the stage. These cones, they hit the mineral in this manner. So the stage is being lighted by these rings. This will be central ring, this will be outer ring, this will be further outer ring. In this manner, the light falls on the stage of the microscope, passes through the mineral section, and the result is that a figure is being produced. So here it has been described how this is the cone. In the main function of the condenser is to produce a cone of light rays. Normally a basal section uniaxial crystal behave as an isotropic mineral under Cross-Nichols, because we know when we take use of the orthoscopic arrangement, or we allow the parallel light rays into the stage of the microscope, these are the parallel light rays. So this is a case of orthoscopic arrangement, and if this is a basal section, light will simply pass through it without any deviation, because in basal section the atomic structure is uniform. So this light simply passes through and is found to be caught up in the analyzer, because analyzer vibration direction and polarizer vibration direction are mutually perpendicular. And here the light which is entering into the mineral section is parallel to the, or these light rays, they are vibrating parallel to the polarizer vibration direction. When they come up, they hit the analyzer perpendicular, that's why no light will pass through. So basal sections under orthoscopic arrangement or in plane polarized light, they show total darkness. But when you talk about the conoscopic arrangement, the light rays are not falling on the basal section of the mineral in this fashion. They are not falling perpendicularly. Rather, the light rays, they fall like this. They fall like so. This is the section. So the rays are falling obliquely to the section. So the total darkness condition will never result as we are getting the darkness condition in Cross-Nichols condition under plane polarized light. Thus, under conoscopic arrangement or in convergent polarized light, the partial section shows a figure which consists of a black or grey area and colored bands because of varying inclination of the rays with the optic axis, which is perpendicular to the section. So you have taken the basal section, to basal section, the optic axis is perpendicular. So the light rings are falling like this. So these rays which occur in one ring, they are all inclined to this optic axis at the same angle. Particularly the light rays which come in one ring, they have same inclination to the optic axis. That's why their optical character becomes same. Similarly, in another ring, all the light rays which come in one ring, they maintain the same angle of inclination with the optic axis. So their character becomes same. So this has been described. The color bands, so the black dark area is found to be produced in this condition. A cross is produced and these are the colorings. Colorings are produced. So this is the figure. So more the light rays which emerge near the center, they are nearly parallel to the optic axis. The light rays which are occurring in the near circle, they are little, if this is the optic axis, this angle, this is the angle of inclination for the first ring. For the second ring, this is the angle of inclination. For third ring, this is the angle of inclination. So angle of inclination gradually increases from the center outwards through these rings. So optic axis is perpendicular to the section and these rays are oblique to it. Let us consider a cone of monochromatic light as shown above. This is cone of monochromatic light and its effect on the mineral section. The rays vibrating parallel to the optic axis, that is MO. This is MO. This is running parallel to C axis and that's why in the analyzer this ray is being cut off, producing a dark center. So MO line will be cut off in the analyzer because it is running parallel to the optic axis. But this light, they have same amount of inclination to the optic axis. So their character will be same and this character will be different from the light rays which come in this ring, and their character will vary from the minerals, the light rays which come in this ring. So likewise the character varies depending upon the orientation of the ring with respect to the optic axis. So the light which is passing through the section in the middle, it is hitting the section perpendicularly, moving parallel to optic axis. So it will be caught up in the analyzer producing a dark center, and this center is called as melatope, which shows the position of optic axis. Optic axis position is indicated by dark spot at the middle. So the light that passes parallel to the optic axis, that passes through the center, it faces no double refraction, and that's why it is found to be caught up in the analyzer, producing darkness. The rays inclined to the optic axis undergo double refraction. The rays occurring in one cone, say MA cone, MA, this cone, first cone, this cone, MA cone, this cone. So this is, say, MA cone, have all the light rays which come in this cone, they have same inclination with respect to the optic axis, and hence undergo double refraction, and each of these rays of light pass through the analyzer and produce interference phenomenon. Because this is the optic axis. Here is the mineral section. So these light rays, they are oblique in a ring. They are hitting the mineral in a ring. Obliquely they are hitting. So this is the path they have covered. And depending upon their path difference, whether the path difference is n lambda or 2n plus 1 by 2 lambda. According to that, the color of the ring will be controlled. It will be light ring or it will be dark ring. It will be light ring or dark ring. So in each ring the character will be same. In other the next ring, the color depth character will be different. So in each ring the character is found to be same because of their same inclination. So this thing has been described here. The rays inclined to the optic axis undergo double refraction. The rays occurring in one cone, say MA cone, have all the same inclination with respect to optic axis, and hence undergo double refraction, and each of these rays of light pass through the analyzer and produce interference phenomena. Depending upon their phase difference, whether odd multiple of half lambda or whole multiple of lambda, light or darkness occur. Similarly, for all cones of light rays, darkness and light result depending upon their phase difference. Thus, result a number of rings of light and darkness around the black center. These rings are called as colored rings, colored curves, or isochromatic colored curves. So what we found? We found a dark center, around it the rings. Ring of 1 wavelength, ring of 1.5 wavelength, ring of 2 wavelength, ring of 2.5 wavelength, like this. We get the rings. So this is the dark center. Light ring, dark ring, light ring, dark ring. Dark ring for whole multiple of wavelength. Color for odd multiple of half wavelengths. So here it will color, here it will color. So in this fashion, we see that interference takes place and color is being produced. The rays of light vibrating parallel to that of the vibration planes of the nickels are extinguished in crossed nickels, and therefore two bars parallel to the vibration planes of the nickels result. This dark cross is called isogar. We know the position of the analyzer vibration direction and polarized vibration, which appears as a cross. This is polarized vibration direction, this is analyzer vibration direction. And the rings of light rays are falling like this. Rings are falling like this. The light rays which are coming on these lines, on these rings, these positions, these positions, these positions, these positions on the ring, the whole surface is being illuminated by rings. So when we move from the center, center is dark, center is indicating the position of melatop. So when we move parallel to the polar directions, we see that light emerging on all these points along this line or along this line, they show their vibrations parallel to crosswire. They show their vibration parallel to crosswire. They show vibration parallel to their crosswire. Or they show vibration parallel to the polars, parallel to the polars. So all the points on these lines, the light rays which come on these lines, they show their vibration in this manner, in this manner, in this manner. So they are parallel to the polarizer and analyzer vibration directions. So this condition is satisfied when extinction occurs. How do we define extinction? Extinction takes place when the vibration direction of the mineral section coincides with the vibration direction of the nickels. So this is the polar direction. This is the polar direction, and this is the mineral vibration direction. This is the mineral vibration. This is the mineral vibration. This is the mineral vibration direction. This is the mineral vibration direction. So we get a dark cross parallel to the polar vibration direction. Thus, we got a central cross, central black point indicating the position of optic axis. We got two dark lines in this manner, and we have the colored rings, light and dark rings. So this is the figure. So a dark cross with center, and these are the colored rings, and this cross is called as the isogyre, and these are the colored rings. Thus, the interference figure shows a dark cross which is called the isogyre, and it is surrounded by colored rings or isochromatic colored curves. If white light is used, the isochromatic colored curves of light and darkness are replaced by the colored rings, which are the complementary colors as found in the quartz waves or in Newton's scale of interference colors viewed under white light. As the inclination of the rays of light are more and more away from the center of the figure with the optic axis, the path difference becomes more and hence the retardation increases and it causes a rise in order of interference color from the center outwards as observed in the quartz wedge. Let me make it more clear. This is the mineral. The light which is passing through the center parallel to optic axis, it covers this much path. The light which is oblique in coming in one ring, it is covering this much path. This light is covering greater path. This covering our still more path. So as we move from the center outwards in the rings, we see that the path difference covered by the light in the rings become more and more as we move away from the center of the ring outwards in all directions. That means the thickness of the section appears to be more as we move from the center outwards in the mineral section. So this light it covers the exact thickness. This the more thickness. This more thickness. So from the center outwards, what happens? The thickness increases depending upon the inclination of the light rays, because the light rays are more and more inclined away from the center. So as you move away from the center, the mineral section appears to be thicker, because here the light rays covers very little thickness. Here a greater thickness. Here a greater thickness. Or as you move away from the center, the light rays they cover more and more path through the mineral. So it appears as if the light rays are passing through quartz wedges, and these quartz wedges are symmetrically placed with their center at the optic axis. So these are the quartz wedges, wedge-like characters presented by the light rays, because in each ring, so here the light of all these which come over this ring, they have same inclination to the center, so they cover same path, this path. So in one ring, the light rays which come over one ring, they cover same path. So their path difference is same. Let us say 1 lambda. The light rings which are coming in another ring, it will be say 1.5 lambda. In third ring it will be 2 lambda. So what happens? As you move from the center outwards, the thickness increases because of the increasing inclination of the light rays from to the same section. Path increases. So the interference color from the center outwards goes on gradually increasing, as is observed when a quartz wedge is being placed in cross-nickel condition and gradually pushed, the interference color gradually rises from one end to the other, or there occurs a rise in interference color from first order to second order, second order to third order, like this. Same thing is being observed in this interference figure from the center outwards. So this will be dark cross, which is isogyre. These are the colorings. The path difference gradually increases. Further the ring from the center, higher is the order of interference color. So this will be higher order interference color. This will be lower order interference color. This will be intermediate order interference color. So this is the figure which has a dark cross and which has a dark center indicating the position of the optic axis. And as we move away from this dark line, so a dark line parallel to the polar directions, and this dark line gradually fades in its color depending upon the inclination of these rays. I have drawn two lines. They make same angle on both sides with this one, with this polar direction. Same angle on both sides, same angle on both sides, same angle on both sides. So the darkness color gradually fades on both directions, because of which the dark cross that we see is presenting a feature like this. Is presenting a feature like this. Thinner at the center, gradually it becomes thicker. So this is this type of isogyre. This is the isogyre, which is thinnest at the melatope and gradually thickens. But very dark line is at the line parallel to the polars. And as we move, this is the portion of two optic axis. So this is the dark line, this is the dark line, but these are the rings, these are the rings. So when you talk about these rings, the angle here, this ring that makes with this line is same on this side. This ring, this angle is same with this angle with respect to these lines compared to these polar directions or analogy directions. So that's why we get a dark cross which is thin at the center and gradually widens away from the center. So in this manner we see the cross, dark cross. Dark cross is not uniformly thick, is thicker like this, it's thicker like this. And this is we know deep shade and partial shade surrounding a deep shade. So this is the straight lines are deep shade, and to certain extent on both sides of these dark lines we have partial darkness, and thus the isogyre presents a look like this. Present a look like this. So this is isogyre. These are the colored rings. Let us have a graphic and analysis of the behavior of light in the mineral section. So what happens to the light rays? So here the light which is coming from the polarizer, let us say it is AB. When it passes through the mineral section, it is being affected by, or it suffers double refraction. Two rays are being produced. Two rays are being produced when they pass through the mineral section. And when they leave the mineral section and enter into the analyzer, each of them are resolved in the plane of the analyzer into two rays, but one of the rays are found to be eliminated, the other rays are found to pass through the analyzer. So if this is one component of light that emerges through the mineral section, it will have its component on the analyzer. This will be the component, and this component from the component of light which emerges from the mineral section, it will have this amount of light in the analyzer. So along this direction this light will go, along this direction this light will go, and they will cancel each other, and this is the case when we talk about the phase difference between these two rays is about n lambda. So this is the analysis for n lambda condition. So let us see what happens to the other case for 2n plus 1 by 2 lambda. How is the graphical analysis? Well, let us discuss this one first. Let certain amount of light represented by the horizontal line AB. This is the horizontal line OAB which is coming from the polarizer. Enter the crystal plate on the stage. Since the ray is now passing through the mineral at an angle with the optic axis, it will suffer double refraction. The light vibrates in planes at two planes at right angles to each other. Let these two directions be AC and AD. So double refracted rays are being produced in the mineral. So they are AC and AD. So out of this light, two rays are being produced in mineral section which are AC and AD. Resolving the original intensity of light into these two directions, we have AC and AD as the values. Leaving the crystal, the light passes to the upper nickel or analyzer, which has its vibration direction at right angles to the polarizer. The ray AC and AD are each resolved into two rays parallel and at right angles to analyzer. The former components A, E and AF pass through, but the latter are annihilated or destroyed. That we know. The analyzer, the very function of analyzer or polarizer is that they will eliminate the one component, that is ordinary component, and allow the external component to pass through, which vibrate parallel to their vibration direction. So AC, so the AC and AD are each resolved into two rays parallel and at right angles to each other in the analyzer, and the former components AE and AF pass through but latter are annihilated. AE and AF. This is AE, this is AF. They pass through the analyzer. Other is annihilated or destroyed. The function of the nickel prism is that will eliminate one of the rays and allow the other set to pass through. This has been described. These rays reach the eye. So these AE and AF, they reach the eye through interference. So they may help each other or they may cancel each other. If they help each other, their amplitudes add up and the intensity of light becomes more. If they cancel each other, then darkness may result. So this is one condition how the light rays are being produced out of this along AE and AF. Now let us see figure 2. So in figure 2, let us see what has happened. Applying the similar construction to various rays in figure 2, we see that all points on any radial line from O have the same intensity. This intensity is at its maximum on the line making the angle of 45 degree with the vibration directions of the two nickels and is equal to 0 when parallel to them. As a result, there will be a gradation of light from the maximum intensity in the diagonal position, that is 45 degree position, to darkness when the vibration planes are parallel to the principal sections with nickels. So this, let us say if in this condition we are getting certain color, so what happens if this condition prevails in any diagonal line? What happens to the intensity of light? Intensity of light in one line is found to be same. Intensity of light along this is 0 because here light is annihilated because the two rays which are produced by double refraction, they are parallel to the polar directions. So no light passes through, this is darkness line. So these are the two dark lines at right angles. So this is the 45 degree position. So here this will be the direction along which there will be maximum intensity of light. As we move from this line to this direction, the intensity of light gradually fades and finally finally becomes 0 here. So this is dark line. Thus, maximum brightness line is the 45-degree line. Maximum intensity is along the 45-degree line. This fact has been described there. So applying the similar construction to various light rays, in figure 2, we see that all points on any radial line, from O have the same intensity. So each line is having same intensity. Intensity is 0 here, intensity is 0 here. Maximum in 45-degree position. So intensity is at maximum on the line, making an angle of 45 degree with the vibration direction of the two nickels. This is analyzer, this is polarizer. Or this is analyzer, this is polarizer. This fact has been described here. So intensity gradually becomes less and less, finally 0 here, 0 here. Analytically, we have for the equation of the intensity of light at any point in a crystal plate between the cross nickels, it is given by this formula. Intensity is equal to r square sin square 2 theta sin square pi n2 minus n1 m by lambda, where r is the amplitude of vibration. This theta is the angle between the vibration planes of the mineral and the polarizer. So this is the angle between the vibration direction and the polarizer. And m n2 minus n1 is the retardation. M is the thickness of the mineral plate. So this gives the retardation. The amplitude and wavelength and retardation remain the same for any circle around the point O. So this equation is found to be reduced to I is k sin square 2 theta. K is the constant, which is found from the retardation, thickness, then amplitude. From them it is being found out, so it becomes constant. So I is equal to k sin square 2 theta. Thus, intensity of light depends directly upon the value of sin square 2 theta. The maximum value of sin of the angle is unity. Consequently, the maximum intensity of light is where sin square 2 theta is equal to 1. From this equation, we get 2 theta equal to 90 degree, or theta is equal to 45 degree. That's why maximum intensity is seen in 45 degree position. So intensity formula is reduced to I is equal to k sin square 2 theta. Sin square theta has a maximum value 1. So it is sin 90 is equal to 1. So 2 theta is equal to 90 degree. Theta is equal to 45 degree. That's why maximum intensity of light is being seen in 45 degree position from the polars. This has been described here. When theta is 0 or 90, when 2 theta is equal to 0 or 180. So these results are same as whole derived from the graphical method already described. So when sin square 2 theta is 0, which occurs when 2 theta is equal to 0 or 2 theta is equal to 180 degree. That means theta is equal to 0 or 90 degree. Thus we get 0, 90 degree position. So here we will find 0 intensity. Here we will find maximum intensity. So in 45 degree angle we get maximum intensity of light. Now coming to the graphical study of the behavior of light rays on the circular section, we find the following two cases. In case 1, for path difference of n lambda, where or p lambda, where p is the whole number. In case 2, for path difference p by 2 lambda, where p is the whole odd number. We know for this case there is darkness, for this case there is a question of help and light. Light is seen here, here darkness. When you talk about white light, for this there is no darkness, we get colored rings everywhere. And the order changes, the order of interference color changes. When we take monochromatic light, this will give rise to dark band, this will give rise to light band. But when you take white light, we do not get this dark band. We get a Newton scale of interference colors. So let us see the graph for this one, and for this one. Let us see figure 3. Expansion of isogyre and the colorings in uniaxial optic axis figure. In figure 3, path difference is n or p lambda, where p is a whole number. And in figure 4, path difference is p by 2 lambda, where p is a whole odd number. In figure 3 here, suppose we are considering the monochromatic light wave at some point on the circle around optic axis. Light waves from the polarizer vibrating in PP plane and with an amplitude OB. This is PP plane, Light is coming from the polarizer with amplitude OB. This is amplitude, this is amplitude, this is amplitude, with OB. This is resolved by the crystal into two sets of waves of amplitude OC and OC dash. This OB is broken into OC and OC dash through double refraction along the vibration direction of the mineral section. If the path difference between E ray and O waves upon emergence from the crystal is Px, P lambda, where P is the whole number, the waves upon entering the analyzer A dash will be resolved so as to cancel each other and yield light waves of zero amplitude. If their path, these two waves, they have been produced out of this through the mineral section, and if they have the path difference is P lambda, where P is whole number, 1 lambda or 2 lambda, like this, in that case their components along the direction of analyzer, they act in two opposite directions and they cancel each other and darkness results. So it has the component along another vibration is like this. This has the component along another direction is this. So these two, they act oppositely and cancel each other, darkness results. This is case of n lambda. And here in figure 4, the opposite situation arises. In figure 4, it is assumed that the crystal produces a path difference of P by 2 lambda, where P is a whole odd number, so that light waves of measurable amplitude are transmitted by the analyzer. Measurable amplitude are transmitted. The amplitude of transmitted light waves is the sum of the individual vectors in the plane of the vibration of the analyzer. So here they help. So OB dash, this is the amplitude of the ray that passes through the polarizer, enters into the mineral section. It is split into two rays, OC and OC dash, as here OB was split up into OC dash and OC. Here OB is split into OC and OC dash, and they, when they enter into the analyzer, they are split up into OD, both. They are, the other part is eliminated, they are split into OD. So both they move in same direction, their amplitude add up, resultant amplitude comes into picture. So this is a case of help, and light is not found to be extinct, but here light becomes extinct. So this is the graphical diagram for P by 2 lambda case. This is the case for P lambda case. Here darkness, here light. Let us study the effects of this figure 4 and figure 3 in azimuth of inclined rings in figure 5. So this is one ring, this is one ring, this is one ring. Let us say the effect is P lambda. In the case when darkness results when you talk about monochromatic light. The vector analysis of effect of conoscope on uniaxial crystal plate in optic axis figure with path difference 1 lambda. This is for 1 lambda. So the case is like this. This is the amount of light coming from the polarizer, splits up into two rays in the mineral section. Their components in the analyzer plane becomes, these are the two components, they vibrate in two opposite directions, they cancel and darkness result. This has been shown here. This has been shown here. So what happens to the amplitude? Let us see. Amplitude in this position will be maximum. Or here, as you see, there is destruction of light, it is dark band. So all through the band we will get the darkness, and the case is like this. But the amount of the amplitude strength will go on, they cancel each other no doubt, but the amount gradually decreases as we move on the ring from 45 position to the polar directions. Now let us take the case of, if we will replace it by white light, we will get color rings. We will never get these darkness rings. So this is for 1.5 lambda path difference. Here the figure 4 case is being repeated all through, and maximum brightness line will be here, and the brightness gradually goes down and here it is 0, here it is 0. No, in this case it will be in maximum position is here. So if we analyze it diagrammatically, it can be seen that it can be seen like this. These are the two rays. This is the another vibration direction. This will be the amplitude of vibration of the two resulting waves that pass through the analyzer plane. So this amplitude, the strength of the amplitude will be maximum in 45 position, here it will be less, here it will be less, it will become less and less, finally it will become 0 here. So therefore maximum brightness position is in 45 degree position. This is vector analysis of effect of conoscope on uniaxial crystal plate optic axis figure. The path reference is 3/2 lambda. In figure 5 vector diagrams, in figure 5, the vector diagrams are located on a circle for path reference of p lambda. P is a whole number and the circle is the circle of darkness or zero illumination for all azimuth. In figure 6, this figure, the light with path reference of p/2 lambda, p odd whole number, it results in the transmission of light waves with the maximum amplitude by the analyzer for an azimuth of 45 degree from the vibration planes of the polars, and the transmission of light waves of decreasing amplitude as the azimuth approaches and coincides with the planes of vibration of the polars. So this is the polar direction, this is the polar direction here, polar direction. So maximum amplitude is here. As we go down to reach the polar vibration direction, it becomes 0. Now here it is a case of darkness when you talk about monochromatic light, but here it is a case of light, and the light brightness gradually comes down to be 0 here, as intensity of light is directly proportional to the square of the amplitude. For a crystal plate cut perpendicular to the optic axis and illuminated by monochromatic light, the result under conoscope is an optic figure which consists of alternating dark circles and illuminated circles which grade around the circles in both directions from the 45 degree azimuths into the more or less diffuse black cross. If white light is used, the illuminated and dark circles are replaced by Newton's scale of interference colors and dark isogyre. So this is when you talk about the white light. So we have the colored rings. These are the colored rings as shown by the Newton scale of interference colors, and this is the maximum brightness line. As we move from this 48 line to the sides, we get that the brightness gradually diminishes. Very dark line here, this is the dark cross, and around this cross we have, these are this is the thickness of the dark cross, because this is the polar direction. So each ring, all the light rays coming over this ring, this ring, this ring, this ring, this ring, this ring, they have the same inclination, same amount of inclination with respect to this axis. That's why if this is the deepest dark line, it will become fainter and fainter in this direction, and it will have a faint line like this on both sides. So it will look like this. The dark band, dark arm of the isogyre will look like this. Similarly, along this direction, it will look like this. And look like this. Look like this. So we have the dark cross, we have the colored rings that has been shown here. These are the color rings. First ring will be for half lambda, then 1 lambda, then 5 lambda, 2 lambda, like this. This is color. This should be all colors, but it should be Newton scale of colors. If you take use of monochromatic light, then it will be first will be color, then dark, color, dark rings. But in particular microscope, we take use white light, so we get Newton scale of interference colors with the maximum bright line in 45 degree position. So this is, so let me analyze the optic axis figure. So we have taken the section perpendicular to optic axis. We have taken a section perpendicular to optic axis. So this is the optic axis. So we have taken a section like this. This section, if we study in plane polarized light, it will show darkness. But here we do not use plane polarized light. We see it in cones of light rays, in convergent polarized light, So what happens when we see it in convergent polarized light? So this is the mineral section. We get the light to be falling over the mineral section like this. So these are the rings of light, and we will get, this is the polar direction, this is the analogue direction. So we will get the cross like this, and this will be gradually thicker. The dark line will be almost parallel to the polars, and to its side shades of darkness gradually fades. Finally it becomes colored. So this is the deep dark, then gradually fades, then color is seen. Similarly, in color, maximum brightness is in 45 degree position. So we see these are the color rings. This is dark isogyre. This is the position of melatope, and this is the optic axis figure in case of UNIAXIAL minerals. Now let us see some of the properties of this optic axis figure, or the main features of this figure. It consists of dark cross, isogyre, concentric with the rings, having 4 wedge-shaped arms widening away from the center parallel to the crosswires. So we have the arms which is widening from the center outwards. These are the 4 arms that together make the isogyre, widening arms from the center outwards. Then this dark cross surrounded by concentric interference colorings in quasi-wedge color sequence from the center outwards. So from the center outwards we see that quasi-wedge colors, thick quadrous colors. First order, second order, third order, fourth order colors, these colors are being seen. On rotation of the stage, the interference figure from the basal section of UNIAXIAL crystals exhibits no change whatever, since the optic axis suffers no change in position. Furthermore, lateral movement of the section produces no change in the interference figure so long as the field of the view is still occupied by the same crystal of constant thickness. So, when this we have taken a section, so this is the optic axis, rings of light are there. So when the stage is being rotated, the optic axis position is found to be fixed. It is not changing. If the mineral is of same thickness, it is shifted laterally. The effect will be same, no change in the shape of the figure. If the figure is being seen within the field of view, thickness same, so when it is being rotated, the position of optic axis is not found to be changing. If the position of optic axis would have changed, then there would have been shifting of the color rings and the shifting of this point. As it is fixed with respect to the rotation of the stage, and the position of optic axis with respect to rotation is found to be fixed. So this isogram remains fixed. It does not show any shift in its position, because when the rotation is being given, the optic axis position is fixed in the section. The arms of the dark cross or isogar remain parallel to the crossed planes of the polarizer and analyzer, and this cross remains unchanged in its position on rotation of the stage. So the arms of the isogar remains fixed because the vibration direction of the mineral section remains the same and it is not changing. That's why the arm will not change. This position will not change. The rings will not change. The color curves are closer and closer together outward from the central axis, because the inclination of the light rays and the length of the path in the crystal increases with the distance from the center. The distance from the optic axis, that is at the center, to the first or any given curve depends upon the several factors, especially the birefringence of the mineral, the thickness of the mineral section, the angle of the aperture of the condenser and the objective. It is of course increased if the image is magnified, as by the use of ocular and Bertrand lens. It also increases with the mean index of refraction of the mineral. So, as you go away from the center outwards, the order of interference color increases, and it is again controlled by several factors such as birefringence value, the thickness of the mineral section, the angle of aperture of the condenser and objective. So these are some of the factors which control the interference color. that we see in the interference figure. In a very thin plates, the interference color rings are absent. If it is thick, so when you see a interference figure, we see the colored rings. More the colored rings, higher is the birefringence, higher is the thickness. If the thickness is very low, very thin, in that case, few rings or no ring may be seen, but this isogar will be seen. Rings may not be seen, or rings, the number of rings will be less. If the birefringence value is low, thickness is low, rings are absent. If the mineral is very thin, the field being occupied by first order grey to white interference color only. In a thin plate, the retardation is very small and hence the interference color is produced is of first order grey. If it is thicker, same mineral, the higher order interference color will be seen, and more number of color rings will be produced, and the rings are found to be closely spaced. Closer are the rings, number of rings are more, and the rings are closer to each other when the thickness is more. The mineral of low birefringence, say quartz, having birefringence value 009, it shows color rings which are hardly seen. Higher the birefringence, as we see in case of calcite, more the color rings, and closer are the rings. The only constant character of the uniaxial rings is their circular character, which results from the cone of light rays. Thus, when you see any uniaxial interference, basal interference figure, we have the color rings. Rings do not change their shape, and we have the dark isogyre, which do not shift its position throughout the rotation of the stage, so long as the optic axis is exactly perpendicular to this section. So isogyre remains fixed, color rings, they remain fixed, shape of the color rings do not change, number of rings is controlled by the thickness of the mineral section, birefringence value. Higher the birefringence value, higher will be the number of rings, higher the thickness, higher will be the number of rings, and the isogyre and the color rings, they do not change their shape, position when the stage of the microscope is being rotated through an angle of 360 degree.